Hey everybody. Man, it's been a great semester with everybody. Cannot wait to see where everyone's going to be headed. But this is our final project, and my name is Andrew Brown.
And I'm Destiny Clowers. Are you ready to jump on in?
Yes, ma'am.
All right, so let's get to the first question.
So, my first question is, can you explain what both the X and Y axis represents in this graph right here?
Of course. So the X and Y axis will be easier to interpret if you imagine this graph being the path that a bouncy ball is taking once it falls off of a table. So you can see in this graph that as X is increasing, Y is slowly starting to decrease. You can know this by looking at the first time that the ball bounces, which is this one right here. And following that bounce, each arch begins to get shorter and shorter and shorter, and eventually this will just turn into a straight line, and that will mean that the ball isn't bouncing anymore. So that means that X represents the increase and Y represents the decrease. So I hope that
Wow.
helped.
Yes.
All right, so now I have a question for you, Andrew.
Okay.
How can you tell if this is truly a function?
So, to answer this question, we're just going to define what a function is. So, a function requires that only one y value be assigned to each x value. This means that there can only be one answer to any question that involves a function. So in this case, the vertical line test can always be counted on to tell you whether or not a graph is truly a function.
Okay.
So you can see that the three vertical lines right here, here's one, here's two, here's three, to tell you whether or not the graph is truly a function. So with these lines that are randomly placed on this graph, they only intersect the graph once. So this means that the graph is indeed a function since the vertical lines don't even intersect the graph more than once.
That's a pretty neat way to tell.
Yeah. All right. So what kind of shift takes place among these graphs right here?
All right, so let me pull up the X and Y axis, and here is our first graph. Our first graph. Here is the second one, which is y equals x squared plus 7, and the last one is y equals x squared minus 7. So as you can tell, the graph of y equals x squared plus 7 is the same graph of y equals x squared, but it's shifted 7 units up. Now, in the same way, y equals x squared minus 7 is the exact same as y equals x squared. It's just shifted down 7 units. Now, in the past, we learned that the x-axis represents the horizontal line and the y-axis equals the vertical line. So since these graphs are identical to each other, they're just shifted up and down, which means they're shifted vertically. This means that this is a vertical shift.
All right.
All right, so Andrew, what is the diameter of a circle?
The diameter of a circle is the distance throughout the whole entire circle. It begins on one side and moves straight past the center and ends on the other side of the circle. In this example, the diameter actually begins at -9, passes through the center, and ends at +9. This means that the diameter is not 9, but it's actually 18 units long. You can also think of the diameter as 2 times the radius if you would. So I hope that answers your question.
Yeah, I was looking at it and it looks like it actually ends on the -10 and the +10. So that means the diameter is actually 20. Isn't that cool?
Oh,
All right.
all right. So does the corresponding angles property take place within this figure right here?
Let's see. In order to answer this question, I think it's important to go over a few of the vocabulary just so you get an understanding of what is going on in this problem. So according to this figure, we have two parallel lines. One is line 1 and the other is line 2. And this means that these lines are never going to touch. They're an equal distance apart from each other and they're never going to touch. And it'll be like this forever. Next, we have two transversal lines according to this figure, which are these lines right here. And this means that these lines, they intersect at one point and then they keep going. So when you have a parallel line that intersects a transversal line, there's always going to be corresponding angles. So that means that corresponding angles do take place within this figure.
Okay.
All right, so what are the corresponding angles in the figure that we just looked at?
This may be an intimidating question, but it's a very good one. Corresponding angles are the angles which occupy the same relative position at each intersection where a straight line crosses two others. So if the two lines are actually parallel, the corresponding angles are equal. With that being said, we have a few in this figure that correspond with each other. We have angles 1 and 7 that correspond to each other. Then we also have angles 3 and also provided 61 degrees, the angle 61 that are congruent. Angle 4 and angle 9 and angles 5 and 12 also correspond. So that answers your question.
Yeah, that did. That helped me understand corresponding angles.
Awesome. My question is, why is the sum of the measures of the exterior angles in this figure equal to 360?
Well, that's a great question, Andrew. Let's think about that. According to the sums of the angle measures in a convex polygon theorem, we know that each of the exterior angles measures will always add up to equal 360 degrees. So here are just a few of the exterior angles, but they actually go all the way around this figure. So let's imagine that we're taking a walk around this figure. So starting at the top, we make our way down this way, and we keep going all the way around. And once we get back to the place that we started, we basically went in kind of like a big circle. And we know that when we go all the way around a figure and back to the top, these angles are going to equal 360 degrees. Now, there's a formula we have to follow, which is the exterior angle formula. So since we just proved that these angles are going to add up to equal 360 degrees, we're going to just take 360 degrees and divide it by n, and n equals the number of sides. So if you count each of these sides, we're going to get 9. So 360 degrees divided by 9 equals 40 degrees. So that means that each of these angles, or the exterior angles down here, are going to equal 40 degrees. Did that help?
Yes.
Good. Okay, so now I have another question for you. What are some other examples of polygons?
Glad you asked. A polygon is a plane figure with at least 3 straight sides and angles, and typically 5 or more. Here is an example. We have a right triangle. We have 3 straight sides and 3 angles. Now, we also have an octagon right here on the right. We have 8 straight sides and 8 different angles that have 8 particular angles. So some other examples are squares, pentagons, hexagons, concave octagons, and the list could go on and on. So those are some other examples of different polygons.
Awesome, thank you.
You're welcome. So what is an octahedron?
So an octahedron kind of sounds scary. We're not used to hearing that big word. But in order to determine the meaning of this, let's just go ahead and look at the prefix. So octa typically means 8, And we know that since octa means 8, this is probably going to have 8 sides or 8 faces, whatever this might be. So we're going to take this triangle right here, and we're going to just count all of the faces on this triangle to see if it adds up to 8.
Okay.
So this first sign is 1, and when we're counting, we're looking at the individual triangles within the big triangle. So there's going to be 8 triangles. So this is the first one. This is the second, the third, the fourth, the fifth, the sixth, and the seventh. Now you might be wondering where the 8th one is, and that is this whole entire face right here. So this face is also 1. And that equals the 8th side, so this is what an octahedron looks like.
Wow.
I know they are kind of confusing, but you just gotta count through it. Okay, so another question for you.
Okay.
The fundamental unit of length in the SI unit is meters. How many meters are in the given lengths?
Okay. So we have a unit on the left side, and we're also going to define the meters on the right side.
Okay.
So starting with the first one, we have a kilometer. Pretty much a kilometer is 1,000 meters. With the next one, we have a hectometer. Now, what that is 100 meters. And in a decameter, there's only 10 meters. And finally, within a decimeter, there's actually 0.1 meters, or 0.1 meter, if you would. Now, you can count, for example, if you had like a 1,000-meter pool, then it'd be 1 kilometer deep. That's a pretty big pool. If
That's
you had a pool that big for the summer, invite me, because we're hanging out.
that's a huge pool.
Yeah.
But yeah, I noticed that deca, is the prefix for 10. So yeah, that
Yeah.
makes sense. That's
Yeah.
cool. Awesome. Thank you for explaining that to me.
You're welcome. So another question that I have for you is, what is perimeter? Can you find the perimeter of this figure right here?
Sure. So first off, let's start with what perimeter is.
Okay.
So perimeter is the border or the outer boundary of a two-dimensional figure. So this means that we can add up the lengths of each side of the figure to find its perimeter. So since this is the outer boundaries of this figure, we're going to add up the numbers on the outside. So 48.0 meters plus 69.0 meters plus 82.3 meters, and that's going to give us our perimeter, which equals 199.3 meters. Now, I did want to mention this 41.0 right here. We didn't add that number because that's actually inside of the figure, and we're only looking for the numbers on the outside, which are the 3 that we added. So
Okay.
anytime you're looking for a perimeter, never add the numbers that are on the inside of the figure.
Okay.
Does that make sense?
Yes, ma'am.
Okay. Oh. Okay, so with the same figure, can you tell me what area is and how you find it?
Yes. Area is the amount of space inside the boundary of the plane figure. In the
Oh,
last question, we saw that perimeter was dealing with the outside of the shape, right? Well, area deals with the inside of the shape. Now, depending on the shape, there are different formulas to find the area. So since our shape is a triangle, the formula we're going to use is A equals 1/2 times base times height. Then we're just going to identify our base and our height, and we'll plug those numbers into the formula to solve for the area. So here we have the base, which is 82.3 meters, and then we have the height, which is in purple, 41.0 meters. What we're going to do, we're going to multiply those together and divide them by 1/2, or multiply them by 1/2, or divide them by 2, whichever way you want to. go about it to find the area. So that's how you solve for area.
That's cool. So that's what you do with the ones on the inside.
Yeah.
Awesome. Okay. Oh,
All right. So how do you find the area of the smaller circle?
all right. So here is our figure, and here's the big circle, and then the little circle is in pink right here. Now, the area of a circle formula is pi r squared. Now, we've went over diameter and radius and all the things like that. So in order to find our radius, we've just got to take half of this circle right here. Now, since the circle is inscribed inside of this square, we know that since the square's length is 10 units, that the diameter of this square is 10 units. Now, since the radius is half of the diameter, we're going to just take 10 divided by 2. We're going to take half of 10, which is 5. And then we're going to just plug that into our formula. So the area of the small circle is pi times 5 squared, and this equals 25 pi units.
Okay. All right.
So anytime you need to find the area of a circle, just use pi r squared.
Okay.
All right, so Andrew, how do you find the surface area for this figure?
Yes. So it may look like a slice of cheesecake.
It
It may look like
does.
a slice of cake in general.
That sounds good right now.
Yes. Yes. So, but that's besides the point. So we have the surface area formula, and all we do is plug in numbers, get the answer. So the formula for surface area is 2 times base plus perimeter times height. To figure out the base, we need to just multiply 15 and 7 together, and then divide the answer in half. To get P for perimeter, all we have to do is add all the sides together. Don't add the height. But when we get the perimeter, we then multiply the height with it, and we get 280. After that, we add 280 with the 105 we got from multiplying 2 by the base, and we finally get 385 meters squared. Therefore, surface area is 385 meters squared. So,
Awesome.
yeah, I hope that answers your question, and you can kind of see it with all the different colors I got going on right here. It may
Yeah,
be confusing, but I tried to color coordinate the base and the perimeter and the height together.
the color coding really helps.
Awesome.
Well, thank you.
You're welcome. Another question. Can you explain why these figures don't have rotational symmetry?
Sure. So let me go over rotational symmetry real fast. This is when a figure can rotate a full 180 degrees around its center and look exactly like it did before it was ever rotated.
Okay.
So each line of the figure is going to match up perfectly. So here's our first figure, which is, I guess you could say, an upside down triangle. And once we rotate it 180 degrees, it definitely doesn't look the same. The lines don't match up perfectly. So this is how you know that this figure doesn't have rotational symmetry.
Okay.
The next is this shape, and this is called a chord. Now, when this is rotated 180 degrees, it looks like that. And once again, these lines don't match up perfectly. If it had rotational symmetry, it'd look exactly the same as it did before it was rotated. So this figure also doesn't have rotational symmetry. And the last figure is another triangle. And once this is rotated around its center 180 degrees, it looks like this. And because the lines don't line up like they're supposed to, that's how we know that the last triangle doesn't have rotational symmetry. So it's pretty easy, the concept of it. You've just got to know how to rotate 180 degrees to tell if it's rotational or not.
Okay.
Well, thank you for asking.
Yeah, of course. Of course.
Now, I have a question concerning rotational symmetry for you. Can
Okay.
you explain why these figures do have rotational symmetry?
Yes, yes. There's actually two more, but it is a great question. A figure has rotational symmetry if it can, like you said, be rotated by 180 degrees around its center and end up exactly in the same location that it had was in before it was ever rotated. All of the lines should match up perfectly after the rotation. So for example, this diamond right here that we have showing, it's in blue. When we rotate it at 180 degrees, it looks exactly like it did before the rotation.
Yeah, it doesn't even look like it was rotated.
Yeah, I know, it's crazy. Same with this rectangle right here. After the rotation, all the lines match up perfectly as if it was never rotated. Isn't
That's
that
so
awesome?
crazy. That's awesome.
Yeah, it is pretty awesome. So last, we have a hexagon. A hexagon also matches up perfectly after the rotation. So this is how you know that each of these figures have rotational symmetry. Because of the 180 degrees, they always line up right before where they started, and it
Yeah,
looks like it's never even rotated.
that's really cool.
Yeah, really neat, really neat.
Oh, well, thank you for explaining that.
Yes, ma'am. What is tiling? Can you give me an example?
Sure, Andrew. So tiling is when you can cover a figure or the whole plane with tiles. So pretty basic tiling tiles. But when you do this, there can't be any gaps between the tiles and none of the tiles can be overlapping. If they are, it is not an example of tiling. So
Okay.
I'm going to try to give you a pretty good example of tiling. So I've started with this hexagon right here, and I added some more hexagons to it around each of the edges. Now, this is tiling so far because there aren't any gaps and there's not any overlapping between these hexagons. And this pattern will also continue when I add another set of hexagons to each of the edges of the previous ones.
That's cool. Looks like a flower.
I know, I love flowers, especially for spring.
The
So that's
spring.
kind of where I
Yeah.
got this example. But as you can tell, none of these lines are overlapping. None of them are causing gaps or anything like that. So if you continued this pattern all the way up, all around the screen, it would continue to look just like this. There wouldn't be any overlapping or any gaps. So I hope that cleared up what tiling was for you.
Yes, absolutely. Thank you so much, Destiny.
You're welcome. Now, this is the last question. I can't believe it. What is an equilateral triangle? Can you find the measure of each interior angle?
Yes. An equilateral triangle is a triangle with the same side lengths and same angle measures.
Hmm.
Everything is equal, hence equilateral.
Oh,
So,
makes sense.
so we certainly can find the measures of each interior angle too. So we know that the interior angles of a triangle must add up to 180 degrees, right?
That's right.
So since there are three interior angles, all we have to do is divide 180 degrees by 3,
Ooh,
and we get the answer of 60 degrees. And that's just going to equal all different degrees, degree points on each side of each corner of the equilateral triangle.
that's really cool.
Yes,
So it'll be like that for every equilateral triangle?
yes.
That is so cool. Well, thank
Yeah,
you.
yeah, no, it's cool.
Okay, so I think that was the end of all of our questions, which means we are officially done with these questions. But if anyone has any additional questions, feel free to reach out to Andrew or I, and we would love to answer those for you guys. But I'm sure y'all are ready to get on with your summer vacation. Y'all probably won't be asking any more questions about math, at least for a while. But do you have anything to say, Andrew?
Well, if anyone's going to build a 1,000-kilometer pool, hit me up.
Yeah, me too. We'll come swimming with you. All right. Well, you guys have a great night, and we will see y'all next year. All right. Bye-bye.